pull back the curtain on the silent hero of your digital life, the operating system. It's this invisible force, this unseen conductor that makes everything on your computer, your phone, you name it, work together in perfect harmony. But how does it actually work? I mean, think about it for a second. That simple click you just made, you just kicked off a super complex chain reaction, a whole symphony of software and hardware. So what's the invisible thing translating your simple click into real action? Well, that's our unseen conductor. So, at its core, an operating system, or OS, is the master manager of your computer. It's the big boss, orchestrating everything from the hardware to the software, acting as that essential bridge between you and the machine. But this sophisticated manager didn't just appear overnight. Nope. It evolved to solve a whole series of really fundamental problems, and it all started with a very, very lonely processor. You see, the first big challenge in computing was this weird paradox. These brand new machines had these incredibly powerful processors, but they were tragically underused. It was kind of like hiring a certified genius, only to have them spend pretty much their entire day just waiting around for paperwork to show up. Early systems were, well, they were simple. They ran one single job from start to finish. The big problem? The processor is lightning fast, but things like reading from a disk or writing to a printer, what we call input/output, or I/O, are just incredibly slow in comparison. The processor would finish its work in a flash, and then it would just sit there and wait. And these numbers right here, they tell the whole story. For a typical program back then, reading a record took 15 microseconds. Writing a record, another 15 microseconds. But the actual work, the number crunching, executing 100 instructions, that only took one single microsecond. So out of that whole 31 microsecond cycle, how much of that time was the CPU actually doing anything useful? A jaw-droppingly low 3.2%. Yeah, you're seeing that right. The most powerful, most expensive part of the whole machine was being productive for just over 3% of its time. The rest, just waiting. And here it is visually. I mean, look at that. It's just staggering. Almost 97% of the processor's time was just gone, wasted. This was a massive, completely unsustainable problem that desperately, desperately needed a solution. And the solution that finally emerged was, frankly, a stroke of genius called multiprogramming. The operating system had to evolve from being just a simple supervisor into a master juggler, totally determined to never let that CPU be idle ever again. The fix was a complete shift in thinking. Instead of running one job all the way to the end, the OS would load several jobs into memory all at once. The moment one job had to wait for something slow, like I/O, the OS wouldn't wait with it. Oh no, it would instantly switch the CPU over to another job that was ready to go. No more waiting. Now, to do all this juggling, the OS needed a brand new concept, the process. A process isn't just a program file sitting on your disk, it's a program in execution. You can think of it like a living, breathing thing that the OS has to manage, keep track of, and give a fair turn on the processor. So how does it manage all of them? Well, by constantly shifting them between different states. A process is ready when it could use the CPU right now. It's running when it's actually on the CPU doing its thing. And when it has to wait for that slow I/O, it becomes blocked. The OS's whole job is to always, always pick a ready process to put into that running state. But, as is so often the case, right? You solve one problem and you create a brand new one. With all these different processes sharing the computer's memory, things got messy. It was like putting a dozen strangers in one giant room with no walls. Total chaos was pretty much guaranteed. I mean, think about it. What's to stop process A from accidentally writing over a critical piece of data that process B needs, or even worse, writing over the operating system itself? The answer was nothing. This memory free-for-all led to bugs, data corruption, and just constant system crashes. And this is where the OS gets really, really clever. The OS basically became an architect, building these virtual walls around every single process. It gave each one the illusion that it had the entire computer memory all to itself, its own private, protected little universe. This incredibly powerful technique is called virtual memory. The OS acts like a constant translator in the background, mapping the private virtual addresses that each process thinks it has to the actual physical addresses in RAM. And the result? Every single process is now safely walled off from its neighbors. This didn't just bring stability, it totally revolutionized software. It allowed programs to be written as if they had access to way more memory than the computer physically even had. Okay, so our processes are now safe and sound in their own little bubbles. Fantastic! But what happens when they need to cooperate? What happens when they need to share something, like a printer or a single file? Well, this introduced the next great challenge, managing concurrency. The complexity was just staggering. As this quote from our source material points out, with so many different things happening all at once, it was simply impossible for programmers to predict every single possible interaction. The OS had to step in and give them the tools to manage all that chaos. Two huge problems started popping up. First, you had improper synchronization, where processes trying to send signals to each other would either miss messages or get duplicates. And second, you had failed mutual exclusion. This is where two processes would try to grab the exact same shared resource at the exact same time, which, as you can imagine, corrupted everything. So the OS had to provide ways to enforce what's called mutual exclusion. The easiest way to think about it is like a rule for a shared bathroom. Only one person can be inside at a time. The OS basically provides the lock on the door, making sure that shared resources are used in a nice, orderly, conflict-free way. But this new protection introduced a very subtle and very dangerous new problem. What if process A has a resource that process B needs to continue, but at the exact same time, process B has something that process A needs? They both end up just waiting for each other forever. They are completely and totally stuck. This situation is known as a deadlock, and it meant the OS had to get even smarter, developing sophisticated algorithms to either prevent this from ever happening in the first place or to detect it when it does and then break the stalemate. And that brings us to the modern symphony. All of these solutions, multiprogramming, virtual memory, concurrency control, these are the fundamental pillars that hold up the complex, multitasking world that we all use every single day. They're the reason you can browse the web, listen to music, and get notifications all at the same time without your device just melting down. Modern operating systems like Windows and Linux are really just different implementations of these same core ideas. For instance, they handle creating new processes differently. Windows tends to build them piece by piece, a more structured kind of approach. Linux, on the other hand, has this really elegant method of creating a near-instant virtual copy of an existing process. Both get the job done, both solve the same fundamental problems, just with different evolved philosophies. From managing a single, lonely processor to orchestrating global networks of billions of devices, the OS has always evolved to solve the next great problem in computing. And that really brings us to our final question. In a world of AI, the Internet of Things, and quantum computing, what grand challenge is waiting just around the corner for the next generation of these unseen conductors?